Okay, so this session is about fatigue, but not so much how to do fatigue. It's about what influences and where we actually need to start when we do any kind of a fatigue calculation. So what we'll discuss will firstly be just the very basics of fatigue calculation in as much imaging as possible instead of equations or too much equations. I'll go through a real life example that shows you some of the complications that we run into regarding fatigue. Then we'll talk about defining events and the mission profile that we need for fatigue, what we need to determine the fatigue life, what impacts it, how to do measurements and fatigue, and how to do Feynman fatigue. And then finally, we'll try and answer the question, if you haven't picked it up by then, where do we actually start when we do fatigue calculations? Okay, so the basics of fatigue is when we have any kind of a structure with repeated loads, at some point we start forming cracks and they grow through the structure. Usually when we talk about fatigue calculations, it's when does the crack start? We're not so much interested in how long it takes to fail, because for high cycle fatigue at least, it tends to be relatively quickly after crack initiation. Here are some examples of a fatigue failure. There's on train wheels again. Some kind of a crane-ish kind of a structure which started with fatigue and then caused collapse. And this bottom right one is what happens when something to do with the train wheels and shafts actually fatigues and fails. Some of the consequences of fatigue. So when we do fatigue calculation, this is just to get everybody on the same page. We've got some kind of a relationship that says we look at stress ranges and ending number of cycles. We've got some kind of a curve that says at this stress level, we'll get that kind of a life. And for the higher cycles, let's say of the order of 10,000 plus cycles, this tend to be a linear curve. So at the end, there may be either a different slope or a horizontal slope if it's an infinite life kind of a metal. At a low cycle, this tend to change, but we actually need to change the strain life. So the methods actually are very similar, whether it's stress life or strain life, is simply whether we plot stress or strain, and some of the equations may differ a bit. If we assume it's this linear, which matches a lot of measurements, we can write some kind of equation that simply says number of cycles is some value divided by whatever your stress is to some kind of an exponent. So that exponent determines the slope, and that k value determines how low this is. So this is for a simple load that keeps on repeating from plus some stress level to minus some stress level repeatedly. The problem is that's not how it acts in real life. So one of the things we also need to take into consideration is mean stresses. So we may find that if we offset it so that it's got a mean tensile load somewhere around there, that's equivalent to a much higher stress amplitude. In other words, the life of this is similar to the life of this. So there's lots of mean stress corrections. I'm showing the Goodman, but there's still a lot of them. Okay, so if I look at the equation for the specifically Goodman, that's the applied stress, the mean stress, the ultimate tensile, and that's the equivalent stress that we need to use if we want to go back to that kind of a method. But that's still not the full picture. We also have in real life some kind of a load variation that it's not constant cycles, varies dramatically over time. And we need to sort that in some way into these subcategories or groups that say we've got so many cycles at that level, so many at this. And for each of these, we can calculate the life, but then we can combine them using the Polgram minor rule, for example, that simply relates to damage. So damage is the number of cycles you've done, let's say that, divided by if I was at that amplitude, how many I could have done to get failure. And Polgram minor simply says I can calculate the damage for each of these sections, add them together, and once they reach 1, it's at the point of crack initiation. Okay, so that's the basic that you need to understand. So stress is important, mean stress can be important, whilst typically it's neglected, but also then we have some kind of a more complex time history of stresses or possibly strain, depending on which method you're using. So let's look at the vehicle, and we'll just look at traveling over different kinds of roads and the effect that will have on the fatigue life of a vehicle. On the left hand, in this, we have a pretty decent quality road. On the right hand side, you see potholes, and that will definitely impact how long it will last on the left hand compared to on the right hand side. But we can also drive over speed bumps, light gravel loads, extreme gravel loads, and if it's severe off-road vehicles, it can go a lot worse than that as well. And each of these will have a dramatically different fatigue life. It may even get to the point where different components actually fatigue based on how the load is transferred. So another pretty nasty one, cobblestones. It's got a pretty repeatable, reasonably close to a certain frequency if you drive at a certain speed, but pretty severe input as well into the system. Okay, so a vehicle can drive over pretty much any of these. And to calculate the life of a vehicle is not quite possible because we don't beforehand know how much of this and how much of this and how much of each of those effectively we have. So this is one of the important bits to understand is this concept of events. Let's call it an event. We're driving the smooth for a certain kilometers over the rougher parts or different parts. And each of those, we can say driving so far over that kind of a road has this equivalent damage effectively. Here's a very simple additional example that's kind of easier in some ways. Simply a conrod, and the stress level of the conrod depends on where in the cycle it currently is, but it's cyclically up and down. And if it's free spinning, there's a slight side load because it comes at an angle for certain point and there's acceleration sideways. But most of the load is in the direction of the conrod. So kind of a buckling load, almost tensile compressive. As the engine speeds up, the stress dramatically increases. If I remember correctly, it's second order with a rotation speed. So driving, just looking at that load at 3000 RPM is 4 times as bad as at 3000. So it's 6000 compared to 3000 is. But in addition, our load level also changes. So if I have part throttle or we're fully coasting, there's very little compressive stress other than, again, due to centrifugal loads. But the moment we have any kind of wide open throttle conditions, there's a significant change in compressive loads as well. So if I want to calculate the fatigue life for something like this, I have to specify at which speed and what kind of a load level I need to do. But the real engine doesn't see that. So a real engine, as we're operating over a wide speed range, we're operating over a pretty significant throttle position range, in other words, load range. And for that, getting to a single number is going to be difficult. Now, just to show you how bad things get when things fail, we started with probably a fatigue crack that was over there, but then after this fell in and started hitting sides, and this effectively caused massive additional damage to the rest of the engine. So this is just to show again how important it is to do correct fatigue calculations or predictions. So just to recap what I talk about when I talk about events and mission profile, the mission profile is what we need to determine the component or the assembly or the design's life. But that is built up of a series of events. Okay, so an event can be, and if I take the previous example, driving, arguments like a kilometer over a smooth asphalt road, driving on a gravel road, and I can have this damage for each of these. I have a certain amount of damage, and I have that damage for every kind of event. It can also be a certain race. It can be driving around one of the gear trade test tracks for a certain distance and a certain time. Okay, so we can then calculate the damage for each of these events, but then we have to specify some kind of emission profile that says, argument's sake, and please don't quote the numbers, this is just thumbsuck numbers. Let's say I've got a small passenger vehicle that I want to design. I may want to qualify so that it can drive 500,000 kilometers over smooth tar roads effectively, 20,000 kilometers of medium or easy gravel kind of roads, and then possibly 500 kilometers of rough gravel road. So that would be my mission profile that says I want to know the damage of 500,000 kilometers of this, plus 20,000 of that, and 500 of this. And if the vehicle, if this is my required, the damage for that has to be less than 1. And that does not even include some kind of a safety factor as well. An easier way to understand maybe is if we look at a train that goes from Sishen to Richards Bay, argument's sake, there's a certain number of left turns and right turns, and each of those have a different radius, and there's so many of the same radius. So we can profile that distance to say there's so many of this kind of, let's say, left hand with a certain radius, so many of a different, each of these effectively is a different event. There may also be rougher parts of the track and smoother parts of the track. But once we have that, we have an indication of the behavior along that track. The second part is it goes full in one way, but it comes back empty. So on the way to Richards Bay, it's full. On the way back, it's empty. So I'll have to specify this is a series of little events that says, let's say we calculate the damage for one radius, but there's 50 of them. I can find the damage total for that per cycle then. So in this case, the mission profile can be a bit simpler because the total for the design may have a specific behavior that says we need to do 1 million cycles, 1 million, which is extreme, but trips from Richards Bay to Sishen and back. But we can also just say, okay, but one complete trip, which is part of a series of separate events, we can combine into an event that's called the trip to Richards Bay and back. Okay, so the mission profile, you get to choose whether you want to pick those events, combine them, and they call that the mission profile, or rather say, I want so many total trips to Richards Bay and back effectively to define it. It's simply slightly different ways of looking at it. Okay, so the next question is, what do we need in order to define the fatigue life of a component? So the first thing is we need stress or strain as a function of time. So stress life would be for ice cycle, so that's we're staying pretty significantly below the yield stress of the material. Strain life is valid in the stress life range as well, but that's typically used when we have plasticity as well. And the life comes down dramatically. But we need stress as a function of time. That's one of the inputs we need in fatigue. The second one is we need some material properties that says how does the material actually behave for a specific for the measured stress ranges and the number of cycles. So this is typical of some steels which have some kind of a cutoff. Now, interesting one year, and that's something we'll just mention slightly, is the measured data is not perfectly on the curves. We tend to have a bit of scatter. So that then effectively becomes part of the last bit that says we also need to have some kind of a settings when you do the calculation. Now, when I talk about settings, we're talking about things like should I do mean stress correction or not? And if I do I use the Goodman methods? Sorry, that's Gerber, not Gerber. Should I not use any at all? There's quite a few additional ones. But each of them determines how effectively we're going from this into this. We also need to pick which stress measure to use. In other words, what is typically assumed when you do fatigue is unidirectional. In other words, pretend we've got a strain gauge stuck at the location we're interested in, and we're using the stress in the direction of the strain gauge. But there's options like sign von Mises, critical plane, there's signed absolute principle, and so on. So critical plane is a method to try and get to unidirectional by specifying a series of different angles, because it's difficult to find the worst angle. So that one simply says, let's look at argument's sake 50 angles and predict the lowest life for any of those. And that then effectively determines what that fatigue life for the component should be. So the minimum of any of the directions is your fatigue life then. Now, some of these settings are maybe prescribed by some kind of a code or standard methods that a company uses. So things like Eurocode 3 and the British BS 7608 and so on have some specific requirements. For example, for welding, you ignore the mean stress. So some of that information will be from there. Some of these does not have a massive difference in terms of answer. They're improvements on something. So again, it'll change your answer, but it shouldn't necessarily double or half the answer. Okay, to recap, we need stress versus time, we need material properties, and we need the fatigue settings that we're effectively going to use. So if we look at the three things we need, the material properties are available for some material types. So there's a few that's typically used in fatigue kind of models, and those may be available. If it's not available, it can be estimated based on yield stress and ultimate tensile stress for some first order results. And if you add a bit of safety factor to that, you can actually get conservative answers and pretty decent answers from there. If you're not certain about the settings, you can do some kind of a bracketing. In other words, try different stress measures, different mean stress correction, to at least give an indication again of how much a specific setting changes the results. So again, by combining these two, we can still get a pretty decent conservative, possibly over-conservative, but we can still get a decent answer, even if I don't know the exact correct settings to use in a specific application. The biggest concern is if you don't have a stress or a strain history, you cannot calculate fatigue load. So that's one of the most important things, is to find out how or where we get that fatigue load. So for that stress history, we need to know if it's something that sees more than one event type, different road types, argument's sake, or in the Conrad example, different engine and load positions. We need that list of events, and then we need results for each of these events, whether it's measured. In other words, let's say I stick the strain gauges on my vehicle and I drive a different roads, or whether I simulate that somewhere else to find that stress for the event. And once we have the event and hopefully the data of what the actual loads are effectively, we need to combine them into a mission profile that says so many of this, so many of that, defines the full behavior of structure, or the full input effectively to the fatigue calculation. So what impacts the fatigue life is pretty much anything that influences the stress history. So that can be from the load perspective, load magnitudes, directions, distributions, and so on that varies. So this can be, in a vehicle's case, the simplest would simply be to look at the vertical load at every one of the wheels. Each of them are independent. There will be a slight dependency depending on the type of road, but still each of those loads effectively is independent. The magnitude of each can vary independently from each other if you really want to as well. Also, the frequency content for that load. So if I have a very specific, let's say very low frequency content, I'm driving over a road that looks like a sine wave, but I'm doing it very slowly, and I'm always in static equilibrium. So that'll effectively change how my vehicle will want to behave and so on, and the kind of measurements and calculations I need to do to get accurate response. The second thing that influences the stress history is how the structure behaves. So things like the actual stiffness of the path, the load path to get from wherever the load is applied to wherever we're interested in, the dimensions. If something is thicker, the bending stress obviously goes down dramatically, or if it's thinner, it goes up a lot. The natural frequencies also change how the structure responds to something that's not at a constant speed and not at a very low speed. So that's where this low frequency content comes into play. Based on whatever the load does, it determines whether or not I have to compensate for that effect. So in other words, whether I can do an equivalent static or whether I have to do some kind of a transient calculation. But the same goes, the damping in the structure also plays a role. So if we operate close to a mode, the response tends to be dramatically more, which means the actual response is critically determined by the amount of damping and the distribution of damping. So let's say we want to do a fatigue calculation by doing some kind of a measurement. So first option, we stick a strain gauge at the location we're interested in. So from there, I get strain, which I can relatively easily convert to stress, which means I can do a strain life or a stress life calculation relatively easily. So yes, we can do it, but we can only do it where we've got the strain gauges. We can use strain gauges to try and estimate what the loads in different locations are as part of some alternative method. Now that's similar to using something like a load cell. So a load cell itself is kind of useless to do fatigue on, at least directly, because what's the fatigue life on in newtons? So what we use this typically for is to find the inputs to a structure and then from there calculate it, the stress or measure the stress at specific locations based on those input loads. So there's a couple of ways to do that, but we can do the same in accelerometers as an input load. Now, the biggest difference between load cells and accelerometers tend to work well at high frequencies, but really bad at low frequencies. But they're really great to do vibration-based fatigue effectively. So it's a bit more difficult to directly relate acceleration to stress, but at higher frequency it tends to work reasonably well. Okay, there's one very big requirement to do measurements. To do measurements, we have to have an existing design. So you cannot do this as part of the design process. You have to do it on the first prototype at the earliest. The one exception would be if I want to drive over a certain road, I already have a vehicle and I want to design something vaguely similar. I can use some of the measurements on that one vehicle as inputs to the second one. But to do measurements, we have to at least have one. Okay, so if you're careful, you can use some of the measurements also for inputs into FEA and do the fatigue calculation in there. So it's entirely possible. It's not too hard. It's just a couple of things you have to double check that you're doing it correctly. If we want to do it in FEA though, the advantage in FEA is we can predict the stress over pretty much the full model. But your stress history is a bit more of a pain because if I simply do a static analysis, it's simply a single stress level. There's no history. So we still have to find what is causing the changes, and we need to model that cause and effect, in other words. So what we can do, for example, is use some kind of a linear combination of FEA. We run a unit load, get a stress state, and if you know the loads from measurements or some other method that you've tried to calculate the loads, we can combine the two and then effectively get a stress history. If we have a known input load to a structure, some kind of a vibration or a driving over a road, we can do modal transient simulation. Now, for reference, that's effectively what Adams does if you use a MNF, a modal neutral form. So even if most of the things are rigid, it still takes the flexibility and the frequency content correctly into consideration. But the alternative also, and that depends on the kind of load that we have, is we can do a frequency response analysis in FEM, combine that with some kind of a PSD as an input, power spectral density, and now we have to do the fatigue calculation in the frequency domain. And the software exists that does that. So it's not too complex to do. The advantage of this is you just need a PSD. You don't need to have any information on what the actual load as a function of time is. So these PSDs you sometimes get out of codes or based on specification for certain vehicle arguments like designs and so on. So that you can then use an input, and your damage that you get is then effectively damage per second, which means you just need to know how long it needs to operate for to find the total damage for that structure. So we can get these input loads directly from measurement. So either at the design stage, but then you have to have a design rather, or if you don't yet have one, if there's some equivalent structure, some equivalent design, we can try and measure on that and use that as information. You have to be careful if it's not exactly the same thing. An example would be if you measure the accelerations, argument's sake, on the the suspension where it attaches to the rim. So other way of saying is the center of the rim, we're measuring vertical acceleration. If the natural frequency for that suspension was, argument say, 10 hertz, and then you'll see 10 hertz pretty dominantly in the response. That 10 hertz now being the behavior between the road and that point. To a lesser extent, also from there to the rest of the structure. If you now redesign the structure to have the frequency that differs from that, and you use it as is, you're actually using the wrong thing because you're exciting it at a frequency which it doesn't like excitement at. So, as I say, you have to be slightly careful with directly using time-based data immediately in that fatigue calculation. In the frequency domain, it's slightly easier because instead of your PSD that you measure, you've got some kind of a curve surrounding that, which extend it a little bit and therefore better represents reality. Now, some codes, some of the MOL standards I know have got PSD specification for certain road vehicles for different road profiles. So that's typically for military vehicles. For normal road vehicles, I think each of the automotive manufacturers will have their own specifications. We also have client specifications sometimes. I know SpaceX and NASA and all of those. If you want to supply a satellite that they have to launch for you, you have to do a couple of tests, and some of them will be you apply PSD in the X, the Y, and Z direction with they specify those PSDs. And that comes from the vibration characteristics and noise characteristics from the launchers that they've measured many of. Okay, and then in some cases, we can also get the loads from something like rigid body dynamics. We run Adam's car model, argument's sake, over cobblestones or drive over a bump, and we get the force history as a function of time, which we can then plug in either again as the linear combination using linear statics, or we can do methods that use the modal transient methods to do the same. Okay, so in other words, when we start with fatigue, events and mission profile is required. And so when I talk about these, mission profile is the sum total of all of the events and how many of each they occur. And some of the information we can get out of these calculations would be some events are not relevant, maybe. So I drive over a racetrack, argument's sake, or a track around Keretek, there's short splits in between where not much is happening, and you can decide whether or not to include it. But we also need to find out how many of each to combine. So once we have the list of events, we need to in some way specify how many of each should be combined to find the total, whatever the time, if effectively the time is that the structure should be. Okay, so once we know which events we'll typically see, if I want to do that either in FEM or measurements, I don't really care. The event type determines what we need to measure and where, or which kind of simulations we need to perform, and what kind of input loads I'll need to add into that. So once we have that, we'll have measured, argument's sake, stress as a function of time. In this case, we'll combine, argument's sake, some kind of a load history with the stress behavior of the structure to get stress as a function of time. So in both cases, we'll have stress as a function of time. So that mission profile critically determines the life of the design. If two people get together and one decides their vehicle design only needs 250,000 Ks on smooth gravel, smooth tar, and another one says about 1 million, each of those will then effectively have a different damage over that design. So that mission profile stays critical. Now, a couple of additional examples would be if I design something like a vibrating screen for a mine. In that case, the actual vibration level is reasonably well defined. It's a function of the excitation level, the mass of the structure, which does vary over time, but relatively little. And then the other event that's actually important and easily abused by mines is the startup and shutdown transient, where we typically operate it at a speed above the first natural frequency, actually probably above the sixth one. If you now start up and shut down, that goes the speed of that imbalanced mass as it slows down will go through all of those modes, and the excitement then causes pretty significant stress, stress at that point in time. Okay, so that's it. Effectively, if I want to design something for a mind, then a vibrating screen, I can do a operating vibration characteristics damage calculation, and I can simply do a shutdown and startup and say, a shutdown and startup cycle equates to this effective total life, because you do not get to decide how many times the mine will shut down and do startups again on there. Okay, so to get back to the start of the presentation, we spoke about what we need to start. And to do a calculation, just in summary, we need material data, we need the stress time history, and some kind of a fatigue method and so on. But the first bit is we need the load history. So without the load history, you can't even start. Once you have the load history, it makes it easier to define which kind, effectively it has to do with events, but which types of events, and then how I plan to measure or simulate them. Okay, so in my experience, over the years, when people asked about fatigue, the most difficult question to answer always was, where do I get the load from? So until you know where to get the load from, it's not even possible to start with fatigue calculation. Okay, so that brings us then to the end of the presentation. Pretty much everything I needed to discuss.